Welcome back, students. In this video segment, we will take a look at section 15.6, triple integrals. Before we get started, a special note. This is probably going to be one of the most difficult sections for the entire course for you. So my recommendation is to spend a lot of time on this, take it real slow, and contact me if you need any help along the way. Okay, I'm available for you almost all the time. Okay, so let's get started. In order to talk about triple integrals, we need to go back a few semesters. Let's take a look at how we developed the integral through your calculus so far. We're going to go back to Calc 1. In Calc 1, in fact, let's do it this way. From Calc 1, what we did is to define the definite integral, we started out with a continuous function. So let's let f of x be continuous on the domain, the closed interval a to b. Okay, let's take a look at what's going on graphically. So graphically, here's the interval from a to b, and we have some function, continuous function, lying above that closed interval. So what we did was we divided up the interval from a to b into n subintervals of equal length. So n subintervals of length delta x, which was the length of the entire interval, divided by n. So that's what we did with the x-axis. And then let's take a look at a typical subinterval. A typical subinterval would lie between, say, x sub I minus 1 and x sub I. And then within that typical subinterval, each of the subintervals, but within that typical subinterval, I pick a point at random and I call it x sub I star. Then I consider the value of the function at that f of x sub I, at x sub I star, the value of the function of x sub I star, and multiply it by the length of that subinterval. And geometrically, that turns out to be the area of the rectangle whose height is the function of x sub I star, and whose width is delta x. Then I took the sum of all those quantities. As I ranged from the first subinterval to the nth subinterval. Then I took the limit as the number of subintervals went to infinity, or goes to infinity. That's the definition of the integral from a to b of f of x dx. And I got a couple of interpretations along with that. If the function was, if the function f is not negative, then this turns out to be the area under the function f of x, and of course above the interval a to b. The area under f of x within the closed interval from a to b. Okay, that was the first application of the integral for you. Something to note is that we have a special case. A special case is if f of x equals 1, then our integral from a to b becomes the integral of 1 dx is just the length of the interval. So equals length of the interval ab, length of the domain. this little special case is an important special case that will come up. In fact, it came up with double integrals. So once we have the concept of the integral defined, we now go to earlier in our course. And if you haven't noticed, I'm bringing us up to speed with triple integrals by going through again the definitions involving integrals so far. So from our course, Calc 3, we defined then the double integral. And the double integral was defined very similarly. So instead of starting with a function f of x is a continuous function on a particular domain, AB, we start with f of xy. Let f of xy be a continuous function. Function on domain D, and D is the rectangle AB cross CD. Okay. Now to find the double integral, if you'll recall, I drew the function and the domain D in the xy plane. I drew it in 3 space. But really, to define the integral, we only need to look at the domain. If we go back to the definition of the integral from Calc 1, we really didn't need to look at the function. All we needed to look at really was the interval from A to B. So that's the case here as well. So to define the double integral, which again, really, we're just reviewing what we did before, all we need to do is to look at the domain of the integral in 2 space. And the domain was the rectangle AB cross CD. So here's our rectangle. Let's say this is the rectangle AB, B cross CD. From there, what we did is we divided up the x-axis. We divided it up into, let's see, m subintervals, intervals of length delta x equals b minus a over m. M as in Mary. Okay, and along the y-axis, we did the same thing, or a similar thing. We divided into n subintervals, of length, equal length, delta y equals length of the whole interval from C to D is D minus C, and then divide by the number of subintervals n. Okay. So along the x-axis, we could then identify a typical x value within that's defining the subinterval. So let's define x sub I, and here's x sub I minus 1. So there's the number I subinterval along the x-axis, and then along the y-axis a similar thing. We could identify the number j subinterval. Here's y sub j. Here's y sub j minus 1. Again, we did this. We did all this before. I just want to bring us to speed because the definition of the triple integral is going to take up right where we left off with the double integral. Okay. So what that did, what the division of the subintervals did, is it divided up the rectangle D into a whole bunch of, it filled the rectangle with a whole bunch of sub-rectangles, and I'm going to identify one of them right now. I'm going to identify a typical subrectangle. And there it is. Okay, so there is a typical subrectangle. The area of that subrectangle is delta A equals its length, delta x, times its width, delta y. Okay. Then what we could do, or what we did, is very similar to what we did in the single integral case. We pick a point randomly within each of the subrectangles. So we pick an x sub I j star and a y sub I j star in that typical subrectangle. There's that point right there. Then, just like we did with the single integral, we took the value, sampled the value of the function at that starred point, just a random point in that typical rectangle, multiplied by the area of that rectangle. In fact, the whole region D is filled with those little rectangles of the exact same area. Then we summed up in the y direction as j ranged from 1 to n, those quantities, f of x sub I j star, y sub I j star, delta A, each of those quantities giving us the volume of a column that went up to the surface. Then we sum in the x direction as I range from 1 to m. And finally, we took the limit as the number of subintervals along each axis becomes infinite. And that's the definition of the double integral of f of x, y, dA over the rectangle D. Okay, very complicated, very complicated sum or limit, actually. Okay, but just as we had with the integral, the single integral, we got some interpretations right off. With the single integral, the integral of the function gave us area underneath the function. With special case, if the function was 1, that the integral gave us the length of the domain over which we were integrating. We have a similar thing going on here. We have that if the function f of x, y is non-negative, then we can interpret the double integral over the region D, rectangle D, as not the area, but the volume under f of x, y, and above the region, the rectangle D. Okay, this was sort of at the heart of our applications for the double integral, and we had a special case. It didn't happen real often, but we did have a special case. If the function f of x, y is 1, then the double integral of 1 dA turns out to be the area of the rectangle of that domain, the rectangle D. Okay, and this extended to other domains, and we'll talk about that in a minute. But this idea that the double integral of 1 gives us area extended to non-rectangular domains. We also got as a really nice result is that the double integral of the function over the rectangle D could be expressed as an iterated integral. Remember, the domain D is AB along the x-axis cross CD along the y-axis. So the really great result was that this resulted to the integral, the iterated integral dx dy is x ranged from a to b, and then integrate with respect to y from c to d, or the integral from c to d first and then from a to b of the function with respect to y and then with respect to x. This is called Fubini's theorem. I'm not sure if I actually gave it a name when we talked about it. I should have, but I seem to recall that I didn't bring up the name of that. So if we're doubly integrating a function over a rectangle, we could convert the double integral into an iterated integral, and that just takes us back to Calc 1. We just integrate two single integrals iteratively. Okay. Then we went from a rectangular domain to various other domains, and this is where the work really began. We went to a type Roman numeral 1 region, which has a function on top, function on the bottom between two vertical lines. And we could kind of go function on top is G2, function on the bottom. I can make a better drawing than that. I'm sure I can. Even I can make a better drawing than that. The type 1 region had a curve on top, a curve on the bottom between two vertical lines. Let's say the curve G1 on the bottom, G2 of x on the top. Then we looked at a type Roman numeral 2 region, which had x is a function of y on the right, x is a function on the y on the left, between two horizontal lines. The function on the right being maybe x equals h2 of y, x equals h1 of y on the left. Then we went to a polar rectangle. The polar rectangle looked like this. It was a section, an area of a sector between two circles. The inner circle being r equals a, outer circle being r equals b. And finally, after all of that, we went to a general polar region, which essentially took the polar rectangle and gave the outer circles a more general shape. The inner curve is h1 of theta, outer curve h2 of theta, between two constant values for theta, alpha, and beta. Okay, and this brings us to our current section. So onto triple integrals. Okay, the single integral started with a continuous function defined on a closed interval AB. Double integral started with a continuous function f of xy defined on the rectangle AB cross CD. We do a similar thing now. Start now with a function of 3 variables. Let f of x, y, z be a continuous function defined, or let's say whose domain is the box B equals A B cross C D cross R S. before we can go any further with this, we got to have a drawing of that box. So I'm going to draw this box. This box is in 3 space, so I'm going to draw it very, very carefully, as carefully as I can. I'm going to draw a box in 3 space. I'm going to get a little help from my surface. That's about all the help I'm going to get. Okay, so here's our box in 3 space. Let's give it a top. Let's give it a back top edge. Let's give it a right top edge. Let's give it a right face. Let's just draw some dimensions inside the box. Drawing the lower edges of the box inside, and then visualize the back edge of the box. Okay, so here's our box in 3 space. I want to put this box, I want to impose some axes. I want to put this box actually in the rectangular 3 space. So I'm going to insert, after the fact, some axes. Here we are. So hopefully you can see in 3 space a box. Okay, so I'm going to make the dimensions of the box, the numbers in this box appear if possible here. So in the XY plane, I'm going to draw the projection of this box, the shadow of this box in the XY plane. The shadow in the XY plane should be the rectangle AB cross CD. So I'm going to come down to the XY plane, and I'm going to draw the projection of the box in the XY plane. Here's A. And come down to the box here. Here's B. So I'm going to continue down to the XY plane. We're now seeing, should be seeing, the projection in the XY plane of the box. Okay, this should finish it off. C to D along the x-axis. Okay, so you should be seeing the projection of the box into the XY plane as the rectangle AB cross CD. Okay, so to give this box a sort of a 3D effect, I'm going to identify the Z dimensions of the box here. So notice I'm going up from x equals A on purpose here. Let's see here. From A, I'm going straight up, and from the back edge of the box, I'm going to that dotted line, and then straight up to the z-axis. This is R. Now from the box, again, I'm going to identify S along the z-axis. So here's R and S along the z-axis. Okay, so hopefully you see a box whose dimensions are AB, or whose is defined by the interval AB cross CD cross RS. Okay, the next thing we do is same as the next thing we did with the other integral cases. We divide up the intervals AB, CD, and RS into subintervals, of equal length on the particular axes. So let's say along the x-axis, we we divide it up into the interval AB into L subintervals of equal length. So L subintervals of length delta x, which should be the length of the entire interval b minus a divided by L. And then I'll picture a typical x value, x sub I, between a and b. That's one of the endpoints of the ith subinterval. Along the y-axis, we'll do the same thing. Along the y-axis, let's do this y-axis. We'll divide into m as in Mary, m as in Mary subintervals of length delta y, the length of the entire interval d minus c over m. And finally, along the z-axis, well, I guess I should put a typical y value along the y-axis. Let's say here's we'll put it right here, y sub j. And finally, along the z-axis, we'll divide it up into n subintervals, n as in Nancy, subintervals of length delta z equals s minus r over n. And here's a typical z sub k as one of the endpoints of those subintervals, those n subintervals, okay? Okay, so what this division does of the intervals a, b, c, d, and rs, it divides up the box B into a whole bunch. We can talk about how many in a minute or so. A whole bunch of sub boxes. It fills the rectangle B with sub boxes of volume delta x, delta y, and delta z. So B is divided into sub boxes of volume delta v equals delta x, delta y, delta z. Okay. So how many sub boxes are in there? How many sub boxes are stuffed into the big box B? Well, we've divided up the x-axis, the y-axis, and the z-axis into L, M, and N subintervals respectively. So there should be L times M times N boxes, little sub-boxes stuffed into the big box B. Okay. I want to draw a typical sub box, and this is rough for me, but I think I could do it. I'm going to draw a typical sub box within the big box B. I'm going to place the box so that one corner of the box is at the point x sub I, y sub I, z sub I, that point. Okay, so I want to place a typical box. I'm going to write this in red. I want to place a typical box, typical sub box, so that one corner of that sub box is at x sub I, y sub I, z sub I. Okay. Actually, I've got those subscripts on y and z not correct. X sub I, y sub j, y sub j, and z sub k. That's better. Okay, I'm going to draw that. So first I'm going to look at the projection of that sub-box in the xy plane. If that didn't make sense, just watch here. From x sub I, I'm going into the rectangle AB cross CD in the xy plane. Here's x sub y and y sub I. And I'm going to increase x by a little bit. And go back into the region, the xy plane. I'm going to increase y by a little bit. Into the region again. So what you should see is a little rectangle in the xy plane. That's the projection of our sub-box that's going to be directly above us in the big box B in the box in 3 space. So I'm going to go up into, from the point xi and yi in the xy plane, I'm going to go to zi, directly up into the box, zk rather, zk in the box. Here's zk in the box. Okay, here we are. And I'm going to create that little sub-box inside of the box B. Very careful drawing on my part. Do this. Here's the top. And this last dimension is not going to appear very nicely. It's okay. I think you get the idea. Let's increase Z by a little bit. Here is a typical sub-box. That little sub-box has length delta x, delta y, and delta z. So if you look back on the x-axis, there's delta x. Along the y-axis, there's delta y. And along the z-axis, I increased, I guess, yeah, that's okay. You increase z by a little bit to get that last dimension. So here's z. Okay, so now we're looking at a typical sub-box within the big box V. This is all just along the lines of along the way defining the triple integral. Within that sub-box, I'm going to choose a point at random. So I'm going to choose within that sub-box, within that one sub-box, within sub-box, choose a point randomly. X sub I, j, k, star, y sub I, j, k, star, z sub I, j, k, star. And I'm going to evaluate my function at that point. I'm going to evaluate my function at that point. Just like in Calc 1, I had evaluated the function at f of x, star, x sub I star. And in Calc 3, with the double integral, I evaluated at the function f of xy at x sub ij star, y sub ij star. I'm going to do the same thing and evaluate my function at f of x sub ijk star, f of y sub ijk star, f of z ijk star. That's just the value of this function of 3 variables at an arbitrary point somewhere in that typical little red sub box in the big box. I'm going to multiply that by the volume of the box. I'm going to start adding up these quantities as I go through all of the sub boxes within the big box B. I'm going to sum in the z direction as k varies from 1 to n, the number of subintervals along the z-axis. Then I'm going to sum in the y direction as j varies from 1 to m, the number of subintervals along the y-axis from c to d. Then I'm going to sum those results in the x-axis as I ranges from 1 to L, the number of subintervals along the x-axis. I'm going to take the limit as the number of subintervals along each axis approach infinity. And my students, that's the definition of the triple integral over the box B of the function f of x, y, z dv. And we're kind of stuck with an analogy a simple analogy to what happened in the Calc 1 and the Calc 2 case. In the Calc 1 case, the single integral of the function gave you the area underneath the function. In the Calc 3 case, the double integral of the function dA gave us the volume underneath the function f in 3 space. Well, we can't do that kind of analogy, a direct analogy for the triple integral, because the function f of x, y, z has no graph as a surface in 3 space. However, we do have an immediate application or thing we can interpret this triple integral as, and we also get that special case when we're triply integrating f of x, y, z equals 1. So one application, this is I think there are a couple homework problems that deal with this. One application of this is this. One application is let f of x, y, z be the density, I should really learn how to spell, density of the box B at x, y, z. And if you're not familiar with density, it's the mass per unit volume. The mass per unit volume of the box at a particular point, which is kind of difficult to wrap your head around if you think about it. How can a point have mass or volume? But we allow this by saying that it's just a really tiny volume surrounding the point x, y, z. If you multiply the density, the mass per unit volume, times, you could think about it as dV as giving you the volume of a very small box. So dV equals the volume of a tiny box whose dimensions are dx, dy, and dz. This is a very common physical interpretation. So f of x, y, z dV, the mass per unit volume times the volume, gives you the mass of the tiny, again with the spelling, mass of the tiny box. so that when you sum up in each direction over the entire box B, the mass of each of the tiny boxes, it gives you the entire mass of the box B. Okay, this isn't of great importance with us right now, but in physics applications, in physical applications, this is a common example. Now there is an important aspect for us, an important application. It's the special case. The special case is when the function f of x, y, z equals 1. If f of x, y, z equals 1, then the triple integral of 1 dv over the box B gives you the volume of the box B. Okay. Okay. We'll be using that special case as our source of a lot of problems on homework and stuff, and we'll be doing some examples in lecture 2. We also have the corresponding Fubini's theorem for triple integrals over boxes. So we also get Fubini's theorem for triple integrals, which allows us to circumvent, to go around having to use that. Look at that definition of the triple integral. Look at the definition. This is what we would be stuck with to evaluate triple integrals. To evaluate triple integrals, if we didn't have some sort of ability to extend the fundamental theorem of calculus from Calc 1 that allowed us not to have to use it, look at Riemann sums like that in Calc 1. So we get that. One of those results is Fubini's theorem. Fubini's theorem says if you're integrating triple E over a box B, and again the box B is AB cross CD cross RS, then we can transform this triple integral into an iterated integral. In fact, a whole bunch of different iterated integrals. We could transform it into the integral first with respect to x, then with respect to y, and then with respect to z after that. From a to b first, then from c to d with respect to y, then from r to s with respect to z. Or any of the other 5 orders of integration. Or any of the other 5 orders of integration. Is the difficulty changed by changing the order of integration? Well, recall what happened in the double integral case. The double integral case very often resulted in integrals of different levels of difficulty depending on the order of integration. Okay, so I'd like to just look at one more example before we dig into the rough part of this section. The rough part of this section, you could probably have guessed it if you thought about it long enough. The rough part of this section is similar to the rough part, the most difficult part of evaluating double integrals. When you were evaluating double integrals over rectangles, the setting up the limits of integration was extremely easy, and that changed when we switched from rectangles to type Roman numeral 1, type Roman numeral 2, polar rectangles, or general polar regions. We had to think a lot more about our limits of integration. A similar thing happens here. We're going to take a look at one example of evaluating a triple integral over a box, and then we'll dig into the meat of this section when we look at arbitrary regions, arbitrary non-box shaped regions. So let's take a look at an example. Evaluate the triple integral over the box B of x squared y dv, where the box B is 0, 1, cross, 1, 2, cross, 2, 3. Okay, so we're going to use Frobenius theorem to do this. Triple integral over the box B of x squared y dv. Then I'm just going to integrate dx, dy, dz. This is purely an arbitrary decision. I don't think the integral varies in difficulty for this particular problem by choosing different orders of integration. So we're going to first integrate x between 0 and 1, then y between 1 and 2, then z between 2 and 3. And the way we do this is a direct extension to how we did this with double integrals. When you integrate with respect to x, that means you're imagining y and z constant. So this sort of like the partial derivative analog, but with integrals, sort of partially integrating with respect to x. So I'm going to integrate x squared y with respect to x. That means y is held fixed. The integral of x squared is x cubed over 3, or 1/3 x cubed. And this is as x varies between 0 and 1, and then we integrate that result with respect to y, and then with respect to z. So we're going to integrate then from 2 to 3 with respect to z after we integrate from 1 to 2 with respect to y. And what are we going to integrate? X equals 1, I'm looking at 1/3 y. If x equals 0, I'm looking at 0 at the lower limit. So antiderivative with respect to y of 1/3 y is 1/6 y squared. Integral of y is y squared over 2. 2 times 3 is 6. And this is as y varies from 1 to 2, and then we integrate that with respect to z. And use the fundamental theorem of calculus on that. 2 squared is 4. So we're looking at 4 over 6, or rather 4 minus 1 over 6, or 3 over 6. And substituting y equals 2, I get 4. Substituting y equals 1, I get 1. So 4 minus 1 is 3 over 6 dz, or the integral from 2 to 3 of 1/2 dz. My 2, my 1, and my 3 just look like 1 or 3. So the integral of 1 with respect to z is 1/2 z, and z varies between 2 and 3. And 3 minus 2 is 1. So this integral has the value of 1/2 with no particular units assigned to it. We don't know what the units of the function x squared y are. We can't really assign any kind of final units to this. So the rest of the lecture involves looking at more general regions. I would suggest that if you haven't had a break, that you take one. The rest of the lecture is going to be quite involved, and you might want to be really mentally fresh when you look at that. So I would suggest a break, or you could continue on with me. So let's look at more general regions than a box B. Let's consider general region, triple integrals over general regions. Triple integrals over more general regions. So let's consider, or let me see if I can draw a typical solid. Here's, it looks like a car. This typical solid, sort of this bean-shaped solid here. This is what I mean by a more general solid. So this is a more typical region we'll say call E. Okay, and the idea, if this is the solid E, is to define and evaluate triple integrals over these solids, these strange bean-shaped regions or whatever, of f of x, y, z, dv. So just as in the double integral case, when we move from double integrating over rectangles to more general regions, we lose Fubini's theorem. We lose the ability to convert the double integral into a doubly iterated integral. We lose we lose that same thing when we start integrating over non-rectangular or non-box-shaped regions. So we're gonna do what we did, a similar thing to what we did with more general regions for double integrals. With double integrals, we looked at Roman numeral 1, Roman numeral 2, polar rectangles, and general polar regions. We're going to do a similar thing here. We're going to look at some special types of regions. Okay, in fact, we're going to take a couple of sections to do this, one step at a time here. We'll say E1. E1 is a type of region where you have a surface on top, and let's say surfaces on top and bottom. So our the surface on top is z equals some function of x and y, and the bottom z equals some other function of x and y. More of that in a minute. The type 2 region, and these are regular Arabic numbers 1 and 2, not Roman numerals. So E1, surface on top and bottom. E2, surfaces in front and back. Surfaces in front and back. And the type 3 region, functions or surfaces on the left and right. Surfaces on left and right. So what am I talking about here? Let's take a look much more carefully at a type 1 region. A type 1 region is one that looks like this. Of course, all of these regions are sets of points in 3 space, but more specifically, they're points x, y, z such that the x and the y come from some domain in the xy plane, and z, remember type 1 region, surface on top and bottom, z varies between a function on the bottom, u1 of x and y, and a function on top, z equals u2 of x and y. Okay, so what does that look like in 3 space? So let's draw this. So I'm going to draw a typical type 1 region in 3 space. In fact, maybe I'll put the axes in last. So here is a surface on the top. I want to do better than that. Here is a surface on the top. So this part of an eggshell on top, and beneath that I have another surface on the bottom. Okay, now I'm going to put in the axes, and here's the projection of this solid, this sort of egg-shaped solid. Here's the projection in the xy plane D. Okay, this is the D in the xy plane. So hopefully you can see that it's definitely of the first type that I mentioned. You have a surface on top, part of an eggshell on top, part of an eggshell on the bottom, and the volume between these two sort of pieces of eggshells. The result, though, that we get is in terms of how we evaluate triple integrals over this E1 region is kind of amazing. The result is amazing. So the triple integral of f of xyz dv, then, and this is pretty nice, the triple integral converts to a double integral over the region D in the xy plane of the single integral from the bottom function u1 to the top function u2 of the whatever you're integrating, f of x, y, z. You integrate that with respect to z. So if it's a type 1 region, you integrate, and that means function on bottom, function on top. You integrate from the lower function u1 to the upper function with respect to z. Z is the direction from lower to upper, from below to above. Then you integrate that dA doubly over whatever region whatever region in the xy plane that the solid region projects into. Okay. Before we go into our other regions, we're definitely going to look at an example, though. So if this doesn't make sense, just stay tuned. So let's look at a specific example. Okay, for this specific example, we're going to look at the special case of the triple integral. Remember that if f of x, y, z equals 1, if we choose the function to equal 1, then the triple integral of that function, dv, over whatever region we're integrating over E, is equal to the volume of E. Okay, so you can pretty much guess what we're going to look at for our example. It's going to be a volume example. So for example, find the volume. Let's say the region in the first octant, that lies between two planes. The planes x plus y plus z equals 2, and the plane z equals x plus y. So just the statement of the problem alone gives you an idea of why this can be so rough. Traditionally, this is considered one of the most difficult, if not the most difficult, part of Calculus 3. And part of that is we really need to see what's going on with the graph of the region. So let's graph the region. The basic idea is to graph the region, then decide if you're going to treat the region as a type 1, type 2, or type 3 region. This one's going to be a type 1 region since it's the only one we've really talked about so far in any detail. Let me clean up my axis a little bit. Let's see here. Okay. I want to redraw this. There we are. Okay. So let's start this again. I'm going to be drawing the region in the first octant that defines the volume we're looking for. Okay, the first of the two planes, x plus y plus z equals 2, is a really simple to graph plane. Remember, to graph a plane that doesn't pass through the origin, just look at the intercepts. The intercepts of x plus y plus z equals 2 are all 2. 2 along the x-axis, 2 along the y-axis, 2 along the z-axis. So let's say this is of our plane. I'll draw in the intercepts in a minute. So here's our plane. Intercept 2, intercepts 2, intercepts 2. So you're looking at x plus y plus z equals 2. Now, the rough one is z equals x plus y. Z equals x plus y is a bit rough because it passes through the origin. And it's kind of hard to draw, at least for me, it's harder to draw planes that pass, it's harder for me to draw planes that pass through the origin for some reason. Well, what I'm going to do is I'm going to break this down into looking at the portion of this plane in the xz plane and the portion of the plane in the yz plane. If you missed that, let's just do it. Z equals x plus y. I want to get that part of the plane that lies in the xz plane. In the xz plane, y equals 0. If y equals 0, that means z equals x, and that's just an equation of a line. Here's z equals x drawn. So that's actually part of the plane z equals x plus y. I'm going to do the same thing in the yz plane. So I'm going to let x equals 0, then I'm going to get z equals y. So here's z equals y. So that's in the plane. I'm going to connect these two, and that will give me a graph of the plane z equals x plus y. So where is the plane z equals x plus y? That's the portion of our surface that lies below. That's this portion that I'm sort of shading in green. This is below. This is the surface below. That's z equals x plus y. The surface that lies above. Let's see. Maybe I'll do that in red. Portion of the surface that lies above is x plus y plus z equals 2. It's this. This is the surface that lies above, the plane above. This can be viewed as a type 1 region where on top we have the red and on the bottom we have the green. And what this is telling us is that we can then use the formula that says that the triple integral of a type 1 region of f of x, y, z dv is the double integral over d in the xy plane. It's a projection of this in the xy plane. We'll get that in a minute. Of the integral of the bottom function of x and y to the top function of x and y of f of x, y, z dz, and then integrate over the projection in the xy plane. Of course, for us, the function is 1. So I'm going to take out that f of xy, the f of xy in the right-hand side. I'm just going to put in 1. 1. Okay. So let's do this. I need the projection of this region in the xy plane. Well, it's easy to see it. See that line of intersection where the red and the green meet? That line projects directly into the xy plane and it divides, it defines the region D as that little triangle in the XY plane. That little region D that I drew in the XY plane is directly below the green surface. If we were standing in D and we looked directly up, we'd see a green plane. We'd see a green plane. Okay, so let's do it. I need that region D. I need that region D. D is the intersection of the red and the green. D is the intersection of the red, x plus y plus z equals 2, and the green, z equals x plus y. So I'm going to substitute the green into the red. I'm going to get rid of z. Since both of these equations must be satisfied at the exact same time, the only way we're going to have this common intersection is if both of these equations are satisfied at the same time. I must be able to substitute the second plane into the first, the green plane into the red plane. If I do that, I get 2 times x plus y equals 2, or x plus y equals 1. So this says we can move forward. This says that we can move forward. Our volume then is the triple integral of 1 dv. That's how this is our formula, the formula we start out with. This translates into the double integral over the region D in the xy plane of the integral from the bottom function of x and y, that's the green function, the bottom function of the function on the bottom, x plus y, to the top function, the red function, was, well, if x plus y plus z equals 2, that means z equals 2 minus x plus y. So 2 minus x plus y. The function we're integrating for volume is always 1. This inner integral is evaluated from bottom to top. That's in the z direction. Then we integrate that result dA over the region D in the xy plane. Okay. Let's move this forward. I need to look, remember, I'm looking at a double integral now. I'm looking at a double integral. The double integral is over D. D is, if we look back at our region in 3D, D is the region that I'm shading in yellow. It's in the xy plane, and it's bounded by the x-axis, the y-axis, and the intersection we just found of x plus y equals 1. So let's take a look at that yellow region, but let's look at it in the xy plane, in the only place it matters. Let's take a look at that yellow region in the xy plane. Okay, let's do that. Here's the xy plane. Here's the line x plus y equals 1. And here's our region D. X plus y equals 1. Now remember, we're translating our triple integral into a double integral, so now we're concentrating on the limits of integration in the double integral. Type D can be considered a type Roman numeral 1 from our previous work, or Roman numeral 2. Perfectly legit to consider Roman numeral 1 or 2. It really doesn't matter. So our volume then equals, we're going to convert this, considering this as a type Roman numeral 1 region, which means function on the bottom, function on the top. And remember, I gave you kind of a hint or or a technique for setting up the limits of putting a line through your region. The green line passes through our type Roman numeral 1 region as y varies from 0 to 1 minus x. Then the x limits, x varies continuously from 0 to 1. And that's our outer two integrals. The inner integral is still the same integral from x plus y to that 2 minus x plus y, and it's integrating 1 dz, the last two integrals type Roman numeral 1, so dy and then dx. So this is a triply iterated integral. The triply iterated integral. Okay, and let's evaluate it. Doesn't take that long. So I'm going to integrate the innermost integral. The integral of 1 with respect to z is z. Z varies from x plus y to 2 minus x plus y. Then we integrate that result with respect to y. Then we integrate that result with respect to x. 0 to 1 minus x. Substituting the upper limit of integration for z. Substituting the lower limit of integration for z. Then we integrate with respect to y and then with respect to x. Let's see here. Let's evaluate this integral now with respect to y. There's a kind of nice thing we can do here. We can keep that x plus y locked in place together. And if we do that, we're looking at 2 minus x plus y minus another x plus y is a minus 2 times x plus y. And I'm not going to distribute the 2 in. There's nothing wrong with it, but I think this technique might be a little nicer than if we just leave the x plus y locked in place. So integrate with respect to y. The integral of 2 with respect to y is 2y. The integral of x plus y with respect to y is x plus y squared over 2. Why is that? X plus y squared over 2. Why is that the case? I'll explain. The reason why that's the case is x is held constant if I integrate with respect to y. So just off to the side here, if you were integrating 3 plus y with respect to y instead of x plus y, and you want to say make u equal to 3 plus y, then this would be a view 3 plus y, because you would be integrating u to u, squared over 2. We could have also integrated it as 3y plus y squared over 2, but there's nothing wrong with holding the 3 and the y locked in place and then integrating with a u substitution of u equals 3 plus y. So for the same reason, don't get too hung up on this. If this bothers you, then you can, if you're so inclined, you can rework this integral from this point and then just distribute the 2 through the x and y, and there's nothing wrong with that. And it's just style. So this integral is, as y varies from 2 to 1 plus x. The 2's cancel. So if I substitute y equals 1 plus x, I get 1 minus x, I get 2 times 1 minus x. Minus, if I substitute 1 minus x in for y, I have x plus 1 minus x squared. That's with that's by substituting the upper limit of integration in for y, If I substitute the lower limit of integration in, the 2y gives me 0, and then minus, so really plus because there's a subtraction in there, y equals 0 gives me x squared. That's substituting y equals 0 in the x plus y factor. Okay. So this becomes the integral from 0 to 1 of 2 minus 2x. X plus 1 minus x is 1. Squared is still 1. Plus x squared. So the integral is shrinking down to something really, really manageable. So this is looking like the integral from 0 to 1. 1 minus 2x plus x squared. Hopefully I haven't made any blunders here. Antiderivative 1, x squared, antiderivative 2x. I'm sorry, antiderivative 1, x, antiderivative 2x, x squared, antiderivative x squared, x cubed over 3. No constants of integration because this is a definite integral. It looks like this should be 1 minus 1 plus 1/3. At 0 we get no contribution, so the result is 1/3. And there are units here. These are cubic units, since this is a physical application or a geometric application of volume. So we're looking at cubic units. Okay. Okay. So something to notice about the type 1 case before we look at types 2 and 3. I want to notice what happens with a typical type 1 case, just to notice. Notice what happened here. Notice that the triple integral by our formula transforms into a double integral from lower function of xy, double integral of the single integral from lower to upper of xy, f of xy dz, and then evaluate that result as a double integral. And if we interpret the region D in the xy plane as a type Roman numeral 1 region, then Roman numeral 1 regions typically convert to a to b with respect to x, lower to upper with respect to y, these are g's, and lower surface, upper surface, xy, and it's the function dz, dy, dx. And there's something that kind of generalizes here. The innermost integral, you integrate z with respect to, you integrate z and then substitute functions with respect to the other two variables. You integrate with respect to z, and the functions in the limits of integration contain the other two variables x and y. When you integrate with respect to y, the limits have the only other variable left with respect to x. When you integrate with respect to x, there are no variables left. So this is very, very, very common. So if you integrate with respect to z, you'll have x's and y's in the innermost integral limits. If you integrate with respect to y, you'll have x in the limits, and you integrate the last one, constants. This is extremely common. Now be careful though that for example, the innermost integrals, they don't have to have both x and y in them, but at most they'll have x and y. The integral with respect to y will have at most x in it, but they could also be constant. So if we were integrating with respect to x, then with respect to z, then with respect to y, then your innermost integral with respect to x would have y's and z's in it, or maybe just y's, or maybe just z's, or maybe just constant, but we'll have at most y's and z's. The integral with respect to z will have y in it, and the integral with respect to y will be constant. This generalizes, and it's just a little something to notice. If this this last note didn't really make sense, it's not imperative. It's not absolutely essential, but it could help. So let's look at the other two types of regions, types 2 and regions type E2 and E3, and then we'll end the lecture with one example that pulls all this stuff together. So just to recap, I think I'd rather recap in black here. Just to recap, type E1 region, set of all x, y, z, such that x and y come from a region in the xy plane. And we have a surface on the bottom, u1 of xy, and a surface z on top, u2 of xy. The type 2 region, and this is the most difficult one for me, because the type 2 region doesn't have a function on top and bottom. It has a surface in front and in back, and it's very difficult for me to draw surfaces that are in the x direction. Nonetheless, it is the type 2 region. The type 2 region considers a projection in the yz plane, dyz plane, of a solid consisting of a surface in front and a surface in back. That means in the x direction. So there's u1 of y and z in back, u1 of y and z in back, and there's x equals u2 of y and z in the front. And I'll make my best attempt at drawing that. So bear with me for a minute here. So I'm going to attempt to draw, bear with me, I'm going to attempt to draw a surface in front, a surface in front. So this is sort of a pipe, kind of weird looking, but this is sort of a pipe. Here's the surface in back. All right. So here's the surface in back. Here's the projection of the surface in the YZ plane. And I might even be able to do better on this. So here's a better attempt, maybe. We'll see. It may turn out to be lame, but we'll find out. Here's a surface in front. That's better. Can't see that. Here's the surface in back. You can see all of that. Here's the surface in back. Here's the projection of of both of these surfaces in the YZ plane. So let me get rid of my first attempt here. Nice fat eraser on this surface here. Okay, so here's, let me get the axes in this picture, in our drawing here. Oops. Let me get our axes. Here's x-axis. That's the worst looking x-axis I've drawn today. Okay. In the YZ plane, you have your region D. the first surface in the x direction, this is x equals u1 of y and z, and the one in front is x equals u2 of y and z. Okay. Now, in spite of the fact that the drawing of these is very difficult, the result isn't so bad. The result looks similar to the type 1 region. The type, if we want to triply integrate a function of x, y, z over the type 2 region, type 2, remember, has function front, function back. It converts into a double integral over the region in the yz plane, so over the back, the projection of this region, solid region in the back, of the integral in the x direction of the two surfaces, between the two surfaces. So from u1 of yz, surface in back to surface in front, u2 of yz, we're integrating that in the x direction, so dx, and then doubly integrate the result in the yz plane, dA. Okay. Let's take a look at the type 3 region, then we'll look at our final example. So the type 3 region looks like this. Let's see, how am I identifying this here? Yeah. Type E3. The type E3 region, again, type 1, surface top, surface bottom. Type 2, surface front, surface back. Type 3, surface left, surface on right. Surface on the left, surface on the right. So it's a set of x, y, z. If you have a surface on the left and a surface on the right, that surface will have a projection in the xz plane, in some domain in the xz plane. And since it's a surface on left and right, that's the y direction. Y will vary from some function of x and z on the left to some function y2 of x and z on the right. Okay, so let's take a look at what that might look like graphically. This one, a little easier for me to draw. This one's a little easier for me to draw. So let me get the axes out. Here's our 3 space. And here is the surface on the left. Here's the surface on the left. Here is the surface on the right. Let's say it's a big old bumpy surface on the right. I'd like to show this a little better. So there's the surface on the left again. Here is our surface on the right. Big old lumpy surface on the right. And here's the projection of the solid that's between those two surfaces in the xz plane, D. And that's ultimately the region D in the xz plane. That's ultimately where our double integral that this triple integral gets turned into is integrated over. If that didn't make sense, don't blame you. So the triple integral over our E3 region, surface left, surface right, of function fxyz dv is the double integral over the projection of our region in the xz plane of the integral from the left on the left, oops, oh my goodness, very sensitive surface. On the left we have y is a function of x and z, y1. On the right we have y equals u2 of x and z. So we integrate from y1 or u1 of xz to u2 of xz. From left to right is in the y direction, so f of x, y, z dy. Then we integrate that doubly dA over the region D in the xy plane. Okay. Now this is a lot of information to absorb. I think that our last example will help to pull all of these results together. Okay, so I've used a little video magic here and I've written out our last example. This last example will serve as I think a good model for you to get started on homework. This homework should take quite a while, and don't drive yourselves crazy. Just take this really slow, and let me know if I can help along the way. Okay, so I've drawn a figure for us in 3 space. The figure shows the region of integration E for our triple integral of f of x, y, z dv. And our job is to set up limits of integration for this integral, viewing E as the different types of regions, E1, E2, and E3. And remember, E1, surface on top, surface on bottom. E2, surface front, surface and back, behind us. And E3, surface left, surface right. So let's interpret this as a type 1 region. Let's view this region E as a type 1 region. So when we view the region as a type 1 region, we need to view this as there's a surface on top, and the surface on top is z equals 1 minus x squared. Z equals 1 minus x squared is a cylinder that extends in the y direction. If you'll recall, if we have an equation representing a surface that's missing a variable, that the surface can be viewed as a cylinder in the direction of that missing variable. So we get z equals 1 minus x squared is a cylinder, sort of parabolic cylinder, in the y direction. The other surface, y equals 1 minus x, can also be viewed as a cylinder, but that's an equation of a plane. It's missing the z variable, so it's a vertical plane. It's a cylinder or vertical or plane that extends parallel to the z-axis. Okay, so definitely the surface on top is the cylinder z equals 1 minus x squared. So our triple integral then is expressible as the triple, again, I'm going to leave out the variables x, y, and z for the function. So the triple integral of f dv is the double integral over the projection of the solid in the xy plane, of the integral from the surface below. Well, our surface, I hope you're able to view this surface as a surface that lies completely in the first octant. And the surface below is the xy plane. It lies within that rectangle pictured in the triangle pictured in the xy plane. So the surface below is z equals 0. The surface above is z equals 1 minus x squared. Surface above is z equals 1 minus x squared of the function. When we're integrating from below to above, we're integrating in the z direction. This is then a double integral dA over the region D in the xy plane. So the rest of our work for this first integral is in converting the double integral to a doubly iterated integral. over the region D in the xy plane. So let's separately draw the region D in the xy plane. From our 3D drawing, we see it's a triangle with the hypotenuse as being, ooh, my goodness, too much coffee. The hypotenuse is the line whose intercepts are 1 and 1. So here's our region D. In 3 space, here's the D, xy plane. In 2 space, in the xy plane, here's the D. Okay. The equation of the hypotenuse is just the equation of the vertical plane, y equals 1 minus x, but it's only that portion in the xy plane, y equals 0. So to set up the limits on the double integral, we can interpret this as a type Roman numeral 1 region, which means we integrate from in the y direction from y equals 0 to y equals 1 minus x. Let's actually do that. The outer integrals then become, let's put on our innermost integral. Actually, we don't need the brackets anymore. So let's integrate the integral from 0 to 1 minus x squared f dz. Since we're interpreting this as a type Roman numeral 1 region, we integrate dy dx. Y varies from 0, look at the little green line, to 1 minus x, and the x values vary from 0 to 1. Okay, we could have produced another integral by interpreting it the projected region in the xy plane as a Roman numeral 2 region, but I think 1 will suffice. We would have integrated, instead of dz dy dx, we would have integrated dz dx dy, but this is okay. So I'm going to skip over the type 2 region and do that last, only because it's the most difficult one for me. I want to get the easy ones out of the way. The difficult ones for me, the difficult region for me is type 2, which is surfaces behind and in front in the x direction, and it's most difficult for me to integrate coming out of the board or coming out of the piece of paper or whatever. Okay, so I'm going to do the type 3 region. Type 3, the type 3 region has a surface on the left and the surface on the right. So let's take a look at our surface. The surface on the left is in the xz plane. So I have a little extra x in my x-axis. Oh, now I got rid of both. The surface on the left is the xz plane. Is the xz plane. If you look at this sort of strange piece of cheese that I have drawn in the first octet, and look in the xz plane, it looks like the surface on the left is y equals 0. This is the actual xz plane that's bounded above by that parabolic cylinder by z equals 1 minus x squared. So the surface on the right, if you imagine going from the xz plane to the right in our region, hits the vertical plane, hits the vertical wall. So the vertical wall will be the surface on the right given by y equals 1 minus x. Let's pull this together. If we interpret this as a type 3 region, the integral of f dv then becomes the double integral of the single integral. Now it's type 3, so surface on the left is y equals 0. Surface on the right is y equals 1 minus x. We're integrating the function. We're integrating from left to right. That's in the y direction. And then we integrate that result doubly, dA, over the projection d in the xz plane. Okay. So just as before, this double integral requires that we understand what our projection looks like in the xz plane. So now I'm going to draw just that projection that I need for the double integral in the xz plane. So in the xz plane, in 3 space, it's the parabola pictured in perspective in 3 space. I'm going to draw that same parabola, 2D. So here's that parabola. The equation of the parabola is just the equation of the cylinder. That curve in the xz plane is just the intersection of the cylinder. Z equals 1 minus x squared when y equals 0. So this is our region D, and let's say xz plane. I don't have to put xz plane, I guess. It's already pretty clear it's in the xz plane. And again, we can interpret this region as either a type Roman numeral 1 or Roman numeral 2 region. My go-to interpretation is Roman 1. I tend to do better, for some reason, integrating from below to above than from left to right. So let's do this. Let's convert this double integral now to a doubly iterated integral with the actually triply iterated integral with our innermost integral f dy. I'm going to be integrating the last two integrals, interpreting it as a Roman numeral 1 region in the xz plane. So I'm going to integrate dz and then dx. Z goes from below to above, and that's what we do in Roman numeral 1. Z goes from 0, little green line, to 1 minus x squared. And then finally, x varies between 0 and 1. Okay, this all takes quite a bit of time to get used to, so plan on spending some real quality time on this in homework. Now I've saved the quote-unquote best for last. Okay, I'm going to interpret this region as a type 2 region. A type 2 region has a surface behind and a surface in front. And not only is this one the most difficult for me, this particular problem has some difficulties in it. So let's get the formula written out. General formula: the triple integral over a type 2 region, formula or function behind, function in front, says we reduce to a double integral of the single integral from the function behind to the function in front. So it's from x of y z behind to x y z front of f, and I'm integrating in the z with respect to x, and then dA double E in the projection D in the YZ plane. Okay, and we've got some work to do. I'm gonna go back to our original drawing, and I'm gonna eliminate that little d in the XZ plane, in the XY plane, and I'm gonna have to look very carefully at my region here. The innermost integral has x behind. The lower limit is x behind, and that's pretty clear. X behind is x equals 0. It's the YZ plane. It's the rectangle. It's x in front that's a problem. The problem is I have two different surfaces in front. I have two different surfaces in front. For part of my surface, I have the cylinder, the parabolic cylinder in front. for the other part of my surface, I have the vertical wall, the vertical plane in front. That the curve of intersection, sort of the curve that I have a little arrow. Oops, I'm still on eraser here. The curve that I have my little, let's say, yellow arrow on right there, which I'll erase in a minute. This ugly little yellow arrow. That little curve is where that little curve is the curve of intersection of the cylinder in the y and the vertical plane and the z, and that divides the surface in front. That's the division of the two surfaces in front. I need to know in the YZ plane where these two surfaces, the projection of that intersection of these two surfaces. So, and I'm going to find that projection in the YZ plane. If you missed what I just said, let me get rid of my yellow arrow, my ugly yellow arrow. I'm going to draw in the YZ plane, in that yellow, the projection of the intersection of the two surfaces in front, the parabola and the vertical plane. I'm going to draw that projection in the YZ plane. So this parabolic shape in the YZ plane, that's the projection back into the YZ plane of my curve of intersection of the cylinder in the y and the vertical plane. That's the projection directly back into the YZ plane of the curve of intersection. Okay. Now I'm going to draw that surface in the back, that little square, again in the YZ plane with the yellow intersection, projection of the intersection. And we're going to use that to get our limits of this region as a type 2 region interpretation. Oops, hang on a second. Here is the YZ plane itself. Okay, oops, sorry about that. Let's get rid of that. Okay. Now here is in the YZ plane. The surface behind. Here is the projection of the intersection of those two surfaces in front. How do I know it's parabolic in shape? That's coming up. So this yellow parabola, the projection of my intersection of the two surfaces, divides the region of integration in the YZ plane into two parts. Let's call it part D1 and D2. And D1 is the projection of this is the projection of the parabolic cylinder into the YZ plane. The region D2 is the projection of the plane into the YZ plane, the projection of the vertical plane. Projection of the vertical plane, call plane, into the YZ plane. So what we're going to need to do with our integral is we're going to need to split this integral up into two integrals. Here's what I mean. We're going to need to split up this final integral that I have above from x behind to x in front into two separate integrals. So let's do it. Let me get rid of this. Okay. Very sensitive surface here. Things keep popping up. I'm barely touching things. Okay. So this integral then, our integral is going to convert to, let's do it, two integrals. It's still a double integral over the region D in the YZ plane, but it's going to be over the region D1 in the YZ plane of the integral of the surface behind, which is just x equals 0, to the surface in front. Well, the surface in front is the cylinder, is the parabolic cylinder, z equals 1 minus x squared. But I'm integrating as x varies from surface behind to surface in front. So I need to solve this. I need to solve this equation for x. Okay, so if I solve this equation for x, I get x squared equals 1 minus z. So x equals plus or minus the square root of 1 minus z. But x is coming out toward us, so x is positive, so square root of 1 minus z of the function f dx, and then this is integrated dA over the region D1 in the YZ plane, plus the integral over D2, that portion of the square projection in the YZ plane, of the surface, the integral of the surface behind, which is still x equals 0, of f with respect to x, but the surface in front of D2 is now the vertical wall, y equals 1 minus x. So the surface in front now is the surface y equals 1 minus x. Okay, but I'm integrating as x varies from surface behind to x varies surface in front. So I need to solve this for x. So x equals 1 minus y. Then I integrate that with respect to a over the projection D2 in the YZ plane. So now back to, how do I know that the shape of the intersection of these two surfaces is that parabolic shape? Well, I'm going to explain that now. I'm going to find that intersection. I need to find the intersection. So I'm going to go back to yellow here just to emphasize what I'm doing here. I'm finding the intersection of the two surfaces. The surfaces z equals 1 minus x squared and y equals 1 minus x. To find the intersection of these two surfaces, I need to substitute one variable into the other. Now the little yellow curve in the YZ plane is independent of x. So that tells me that with these two equations, I'm going to eliminate x by solving one of the equations for x and substituting into the other. The simplest one to solve for x is the second one. So x equals 1 minus y. Then substitute that value back into z equals 1 minus x squared to get z equals 1 minus y quantity squared. How do I know that the shape is a parabola? Because that's the equation of a parabola. If we expand, we get z equals 1 minus the quantity 1 minus 2y plus y squared, and then distribute the -1. So we have z equals 2y minus y squared. That is the actual equation of that yellow projection of the intersection of the two surfaces into the YZ plane. And we're ready to finish this up, believe it or not. This is as difficult as this gets. But it does get this difficult once in a while. So, okay, so I'm gonna make us a little room here. I'm gonna kind of block this stuff off here. Okay. So our triple integral then becomes, let's do each one. D1 can be considered a type Roman numeral 2 region, function below, function above, and so can D2. So I'll try to do our first integral. I'll draw a little green line through our region type. So I'm going to interpret this as a type Roman numeral 2 region. So our first integral is then transformed into an iterated integral. The innermost integral doesn't change. So it's 0 to 1 minus zf dx. But dA now, since we're interpreting this as a type 2 Roman numeral 2 region, it's dz, lower to upper, dy, left to right. Look at the little green arrow. Z goes from 2y minus y squared to 1. Z equals 1 along the top edge of that box. And then finally y varies continuously between 0 and 1. The last integral, the integral over d2, double integral over d2, is another type Roman numeral 2 region. The green line going through our region. The innermost integral doesn't change. It's the integral from 0 to the square root of 1 minus z. This isn't part of the limits for the double integral. We're again interpreting it as type Roman numeral 2, so it's dz dy. But this time z varies, look at the little green line, the second green line varies from z equals 0 to the parabola, 2y minus y squared. And finally y varies continuously between 0 and 1. And that is an example of a type 2 region, And that ends this video segment. So start digging into homework on section 15.6, and I'm looking forward to talking with you again soon.